Hello everyone, we are discussing moisture transmission related aspects of clothing comfort. So, we know that moisture transmission through textile material takes place in two forms. One is liquid water form, liquid water transmission, and the moisture in vapor form. So, liquid water transmission we have discussed in detail in last segment. So, in this segment we will discuss the moisture transmission in vapor form. So, if we see if we compare the moisture transmission in liquid form and moisture transmission in vapor form, the principle of transmission, the theories of transmission are entirely different, and the moisture gets transmitted through the textile material, textile media at two different form at two different activity levels. So, for a normal activity level, most of the moisture gets transmitted in vapor form, and in high activity level it gets transmitted in sweat form. Now, we will discuss the moisture transmission in vapor form. So, moisture transmission in vapor form, moisture vapor transmits through the fabric primarily in through the inter yarn space and through inter fiber space. So, in this two zone, through this two zone, moisture in vapor form gets transmitted, and moisture vapor diffuses through the air space between the fibrous material. So, open fabric structure promotes the diffusion. So, if there is some open space, so moisture gets diffused through this. Now, try to see what are the different layers through which the moisture gets transmitted. So, moisture vapor from our human skin, from our skin gets transmitted to the evaporating fluid layer. So, just above the skin, just below the fabric layer, there is a layer which is called evaporating fluid layer, then it comes inside the fabric layer. So, through fabric layer moisture gets transmitted, and the transmission through the fabric layer takes place by different principles we will discuss, and our main focus of discussion will be this part where moisture gets transmitted through the fabric layer from one layer to another layer, and above the fabric layer it is a boundary air layer, and this layer is very important. If the moisture concentration, vapor concentration at this layer is high, then that will affect the moisture transmission of the fabric layer. Okay. And this boundary layer is connected with the effect, this is actually influenced by ambient air layer. So, if the ambient air layers the moisture level, if it is saturated, then boundary air layer will definitely will be affected, and so the fabric air layer will get affected. So, all the layers will get affected. So, the total balance has to be there, then proper transmission of moisture vapor from humans, our skin to the ambient layer will take place. Any of the layers, if there is some problem, then that moisture transmission will get affected, and most important which we can control is our fabric layer. So, we will see that how the fabric structure of fabric, structure of yarn, even type of fiber affect the moisture transmission behavior through this fabric. So, basically if you see the moisture transmission through the fabric layer, it takes place by actually it follows 4 mechanism. Okay. So, this mechanism, mechanisms are diffusion. First is diffusion of water vapor through the air space between the fiber. So, diffusion takes place through the air pockets. If air pocket is not there, so fabric is totally compact, solid material, so there will not be any diffusion. For diffusion to take place, so there has to be some air pocket. So, that if we can create air pockets within the fabric structure, then we will enhance the moisture vapor transmission through diffusion, which is very predominant principle of moisture transmission through textile material. Next is that absorption, transmission and desorption. So, this only takes place for hydrophilic fiber. So, hydrophilic fiber material, it absorbs the moisture and moisture gets transmitted through the material, through the fiber and to the other surface, where the vapor pressure is relatively low, and from there it gets actually evaporated, dissolves. So, this is the principle, and if we compare the diffusion principle and the second one, absorption, transmission, desorption, the diffusion through air is very fast. It is much faster than absorption, transmission, desorption. But diffusion, this second principle is very important, where diffusion is not there. So, that is we will discuss. And third is adsorption and migration. So, fiber is not absorbing the moisture, but it gets adsorbed at the surface, and from the at certain temperature, adsorption takes place at certain temperature, below certain temperature. At high temperature, it actually moisture droplet does not occur. So, that adsorption is not, that does not take place. So, after the moisture gets adsorbed at the surface, then the moisture is transmitted along the surface. Okay. And last one is that it is a forced convection. So, like forced convective heat transmission we have seen, similarly here the air, flow of air transmits the, it enhance the moisture transmission. So, boundary air layer outside the fabric, above the fabric layer, as we have seen in last slide. So, if the air blows, so at air, as the air blows, that will take the all the moisture beyond the above the fabric surface, and so forced convection will take place. Now, we will start the first principle of moisture transmission, it is a diffusion. So, diffusion, it is basically the vapor pressure which is the driving force. So, if the vapor pressure is created, the vapor pressure gradient is created, that will actually drive the moisture vapor. So, vapor pressure gradient acts as the driving force, occurs on a molecular level at low speed. So, it is basically it is at a lower speed, it cannot take place at high speed. So, it at a lower speed, so moisture vapor pressure gets generated due to the presence of moisture, and it pushes the moisture that vapor to the other surface. So, depending on the pressure difference, the moisture gets transmitted. So, moisture vapor is transported from the higher concentration zone, where the vapor pressure is high, to the lower concentration zone. So, it follows the Fick's law. As per the Fick's law, the relationship is between that is the moisture flux. This is the moisture flux is equal to the dAB, which is the diffusion coefficient, by and it is a concentration of moisture vapor, and this is the distance between the distance, that is the length. So, depending on the concentration, So, moisture flux at higher concentration the moisture flux will be more. So, that the difference in the concentration of moisture, the moisture which actually the concentration gradient, this is the concentration gradient which is the driving force. So, it is proportional to the heat flux, and the diffusion coefficient or mass diffusivity is actually it is of one component diffusing through another media. So, this is the DAB is the mass diffusivity. So, moisture rate of moisture transmission in terms of gram per square meter per second, it is proportional to the concentration gradient dCA by dx. This is the concentration gradient, vapor concentration gradient. So, the diffusion which follows the Fick's law, so that is called Fickian diffusion. And Fickian diffusion takes place through the air pockets. Only if we can create the air pockets within the fabric structure or yarn structure, then diffusion will take place. In this case, the diffusion coefficient does not alter with the change in moisture vapor concentration within the material with the change in temperature. So, this diffusion coefficient, the constant, it does not change with the temperature and moisture vapor concentration. In the case of air permeable fabric and microporous polymer, this type of diffusion takes place. So, why air permeable fabric? In air permeable fabric there are pores available. So, that through the pores, depending on the moisture vapor concentration gradient, the moisture vapor gets transmitted. And similarly, why microporous polymer? In microporous polymer, the moisture gets the pores are get filled with the moisture vapor, and as soon as the moisture vapor pressure is more than the ambient air on other side, so that moisture will get transmitted. So, the vapor pressure gradient has to be created. As soon as the moisture vapor gradient pressure gradient is created, the moisture gets transmitted. So, in addition to the Fickian diffusion, there is another diffusion which is called non-Fickian diffusion. That means, the material, the process where the Fickian diffusion is not followed, means the only vapor pressure, Fickian diffusion takes place through the vapor pressure gradient. So, the diffusion which does not follow the law, this actually Fickian law is called the non-Fickian diffusion. The water vapor transmission rate of the hydrophilic polymer confirms the following relations. That means, for hydrophobic polymer normally it goes through the air pocket, the air moisture does not get absorbed by the polymer. So, the Fickian diffusion takes place, but when we use the hydrophilic polymer, then the hydrophilic polymer suppose it is a solid polymer, it is a polymer and it absorbs the moisture, and then through the material it gets transmitted to the other surface. So, water vapor transmission is equal to D, where D is the diffusion coefficient, okay, is the amount of a particular substance that diffuses across a unit area in 1 second under the influence of a gradient of 1 unit. So, this is the diffusion coefficient, and P1 minus P2, these are the partial pressure gradient between the two surfaces. So, there are any polymer surface material is there, in between two surfaces there are pressure difference P1 and P2. P1 is the surface of the higher pressure and P2 is on the other side, and D is the diffusion coefficient and S is the solubility coefficient that means the volume of gas that can be dissolved by a unit volume of solvent. Now, this is important for a textile material. Here we are talking about, we are not talking about the gas, here we are talking about the a moisture vapor. This non-Fickian diffusion, it is basically for a gaseous material. So, this S is the solubility coefficient of gas here, but in our case it is a moisture regain of textile material. So, as the it is equivalent to moisture regain of the textile material, and L is the thickness of the material. Now, if we see a moisture of a hydrophilic fiber in suppose a cotton fiber, fabric is made of cotton fiber, and if we assume that there is no pores are not available here. So, what happened in that case, the moisture vapor diffusion takes place through non-Fickian diffusion. It moves through the structure of the fabric, which is actually it is very close to our absorption desorption principle. The hydrophilic material transfers water vapor according to non-Fickian diffusion. So, that for hydrophobic material like polyester, if we see the transmission of moisture vapor through Fickian diffusion, but transmission through cotton fabric is basically both by Fickian and non-Fickian diffusion. The Fickian diffusion takes place through the pores, whatever pores are available, through that the Fickian diffusion takes place, and if there is no pore, so in that case the non-Fickian diffusion will take place. So, non-Fickian diffusion is, if we see, it is very slow in nature. So, moisture vapor can diffuse through a textile medium by two principles: the simple diffusion through air space within the fibrous structure, it is a Fickian diffusion, and diffusion along the fiber itself, it is a non-Fickian diffusion. So, if we see the most of the textile material, they have some moisture absorption, moisture regain. So, the textile material, it moisture transmits through the textile material in using both the principle Fickian diffusion and non-Fickian diffusion. Depending on the moisture absorption, hydrophilicity of the fiber, the Fickian and non-Fickian, and also depending on the air space present within the structure, which principle will be predominant, that actually is controlled. Okay. So, if the air space is more, that means the Fickian diffusion will be predominant. If the hydrophilicity of the fiber is more and air space is very less, then non-Fickian diffusion will take place. So, moisture vapor diffuses from one surface of the fabric to the surface of the fiber. I am talking about the non-Fickian diffusion, to the surface of the fiber, then travels along the interior of the fiber, reaches to the other surface of the fiber, and from there it gets evaporated. So, this is the process, and if we see moisture is reaching to the surface of the fiber, it gets penetrated through the structure, fiber structure, it is reaching to the other surface, and from there it is getting evaporated. This is one principle of non-Fickian diffusion. Another principle is Fickian diffusion, where pores are already present in the structure. Moisture vapor with higher pressure gets it is penetrated inside the pore gradually, and vapor pressure is developed there, and that vapor, as soon as the vapor pressure is more than the other surface, vapor pressure of other surface, that will get transmitted. So, if we see the Fickian diffusion is very simple, and straightforward. So, that is why it takes much less time than the non-Fickian diffusion, and non-Fickian diffusion to take place, non-Fickian diffusion, if we see at a specific concentration gradient. So, if we see the concentration gradient is same. So, our from the skin and to the atmosphere, if the concentration gradient is fixed, if we see the diffusion rate depends upon the porosity of the material, what is the porosity of the material, and water vapor diffusivity of the fiber. So, and diffusion coefficient of water vapor, if you see through air it is much higher than through cotton fiber. So, here if we consider it is a cotton fiber, diffusion through cotton fiber is 10 to the power minus 7 square centimeter per second, whereas through air it is much higher, 0.239 square centimeter per second. So, what is here? The porosity of the material, it is controlled by the diffusion through air. So, if we can increase the porosity, the diffusivity will increase, and this diffusion is by Fickian diffusion. So, Fickian diffusion is very very high. So, if we have to increase the, if our vapor pressure level is very high, if we have to eliminate, if we have to remove the vapor at higher rate, we have to follow the Fickian diffusion, and for that we have to create the air pocket, we have to increase the porosity of the material. If we see that our vapor pressure is generated, or vapor pressure gradient or generation of our vapor pressure is slow, very low, in that case we can depend on the water vapor diffusivity through the fiber. So, in that so the situation is that at very low activity level, if we have, suppose if we wear two different fabric highly compact, say with zero porosity, polyester filament fabric, another is the cotton fabric made of cotton fiber, cotton fabric, very highly compact fabric, two fabrics, and we are sitting idle. So, because that means we are generating the moisture vapor only. So, if we consider that porosity is least, let us for argument we consider the porosity is 0. So, when porosity is 0 for both the fabric polyester and cotton, in that case polyester will not have the non-Fickian diffusion, if we consider polyester is hydrophobic fiber. So, in that case polyester is not absorbing any moisture, it is not transmitting. So, in that case even if we are sitting idle, polyester will give uncomfortable sensation, because the insensible perspiration whichever we are, whatever we are generating, it is not getting transmitted. But cotton, although it is very slow, transmission rate is very slow, but cotton will have comfort feeling because of the non-Fickian diffusion through the fiber. Okay. So, depends on the rate at which moisture can diffuse into and out of the fabric. Okay. So, this actually at very high rate if we consider, in that case cotton will fail, in that case you have to generate some pores. So, we have to create the Fickian diffusion. Okay. The moisture diffusion through air portion of the fabric is almost instantaneous. So, we have to create that air, whereas through fabric system it is limited. Okay. So, it is instantaneous, it is slow through the fiber, which is due to lower moisture diffusivity of the textile material. Okay. And in the case of hydrophilic fiber assembly, vapor diffusion does not obey the Fick's law. So, that is the way it is a non-Fickian diffusion that we have discussed. But hydrophilic fibers, our advantage is that if we can create the air pocket, the Fickian diffusion also take place. So, diffusion along the textile materials, two stage diffusion. In the case of hydrophilic fiber assembly, two stage diffusion take place. So, hydrophilic say cotton fiber, cotton fabric. Okay. First stage is a Fickian diffusion through air gap, as we have discussed, and second stage it is much slower, follow an exponential relationship. Okay. That is a non-Fickian diffusion between the concentration gradient and vapor flux. It is very slow. Diffusion of vapor through fiber causes absorption of moisture. So, it creates another problem. So, when the hydrophilic fiber, so when non-Fickian diffusion take place, so due to absorption of moisture, the fiber gets swelled. So, it sometime it slows down diffusion. The slows down diffusion means it is a which diffusion? It is a Fickian diffusion. So, non-Fickian diffusion also affect the Fickian diffusion by slowing down by reducing the pore volume. So, fiber with like cotton fiber is an example where when it slows down, when it swells up. So, it slows down the Fickian diffusion. Okay. So, now let us see what are the factors which actually controls the diffusivity. So, diffusivity of any material of textile fiber particularly decreases with the increase in fiber volume fraction, that means a proportion of fiber in the fabric. That means, that means air pocket, volume of air pocket is reduced. So, when the fiber volume fraction increases, the air pockets proportion of air pockets reduced. So, diffusivity reduces. So, this diffusivity it is due to Fickian diffusion. Increase in the flatness of fiber cross section. So, this is important. What happens if the flatness increases, it is like a deviation from roundness, that means the specific surface area if it is increasing, then what happens? It will actually drag the flow. It is similar to the air flow. So, air flow, if the specific surface area is increased, it will drag the flow, free flow of the moisture vapor, and the diffusivity decreases, and it also decreases with the increase in fabric thickness. So, as the fabric thickness increases, the flow path will be longer. So, the diffusivity of the fabric decreases, also this is reducing the porosity of the fabric, and water vapor diffusivity has direct correlation with the air permeability. So, all these factors if we see, these are related with the air permeability. So, by measuring the air permeability of a fabric, we can actually indirectly get some idea about the diffusivity, at least the Fickian diffusion. So, non-Fickian diffusion is something else, which actually where moisture gets absorbed by the fiber, and diffusion coefficient if you see, it depends on the two factors. One is the temperature of the system, atmosphere, and also the pressure. So, at higher temperature, the atmospheric temperature, diffusion coefficient is high. At higher pressure, diffusion coefficient will be reduced. So, if the temperature is increased, the environmental temperature is increased, the diffusion coefficient will increase. That means, it will have higher diffusion. So, and if we increase the atmospheric pressure is increased, so diffusion will be slowing down. So, in general, the diffusion coefficient of fiber increases with the increase in concentration of water in the fiber. So, if the water concentration inside the fiber increases, the diffusion coefficient also increases. So, after diffusion, next principle of water transmission is sorption, transmission and desorption. It is an important phenomena of moisture vapor transmission, which is responsible for maintaining microclimate during the transient condition. So, that we have already discussed that the non-Fickian diffusion. So, it maintains hygroscopic fiber material absorbs moisture from human skin, absorbing fabric work as a moisture source to the atmosphere. So, it absorbs moisture and then it is actually it absorbing fiber, it gets transmitted to the other surface and release of moisture. So, the difference here with the Fickian diffusion and this absorption, transmission, desorption is that in Fickian diffusion moisture gets absorbed by the fiber in vapor form, but here it is basically in the at high concentration of the moisture. Here it absorbs, the moisture is absorbed by the fibrous material from the human skin and it gets transmitted through the fiber structure, okay, through the fabric, and in earlier case it was the through one fiber. Reduce moisture, it reduce the moisture built up in the microclimate. So, as soon as it absorbs the moisture from the microclimate, it reduces the moisture built up. So, our skin become dry. Okay. So, this process enhance the transmission of moisture vapor from human skin to the environment. So, that way it absorbs. The transmission of moisture vapor at low activity, that means in case of hygroscopic material is higher than which do not absorb. So, that means the at low activity level the hygroscopic material absorbs more moisture than the fabric fiber which does do not absorb. That is why this phenomena is for that cotton is comfortable at low activity level, where polyester is not. That means that it does not absorb moisture at low activity level. During absorption desorption process, absorbing fabric works as a moisture source of the atmosphere. So, that is why it actually always the absorbing fabric, when it absorbs moisture from the human skin, it is always it acts as a moisture source to the environment. It always release moisture to the environment, and it also acts as a buffer. That means, it maintains the constant vapor concentration always in the around the surface. Okay. A constant humidity is maintained in the adjoining air, through though the temperature change due to the heat absorption. So, it maintains the constant moisture vapor concentration, because it is a constant source of moisture. Next comes the next phenomenon, it is adsorption and migration. So, adsorption of water molecules takes place below critical temperature. So, adsorption normally at high temperature it does not take place. So, at below some critical temperature the moisture droplet forms. So, at below critical temperature van der Waals force occurs between the moisture vapor molecule and the solid surface of textile fiber. So, that force comes into picture. The higher the vapor pressure and lower the temperature, higher is the amount of adsorption. So, at lower temperature and higher vapor pressure, that amount absorbs and by the van der Waals force will be high. So, adsorption will be more. So, this only adsorption takes place at the lower temperature. So, the factors which affect the adsorption, so amount of moisture adsorption depend on the moisture regain of the fabric. So, that means, a fiber with high moisture regain, it will absorb the moisture. So, adsorption will not take place. So, for cotton fiber, adsorption principle will not take place, it will be absorption desorption principle. But for polyester, for any hydrophobic fiber, okay, this principle will, when absorption desorption principle is not taking place, in that case the adsorption and transmission will take place. So, fiber with high moisture, this is not the only condition, but high moisture again will immediately absorb the moisture. So, fabric with low moisture again at high humidity level, if the humidity level is low, then the adsorption will not take, because the droplet will not form. The quantity of humidity should be high, the moisture vapor should be high. So, the adsorption takes place at high humidity level. At high sorption hysteresis, the adsorption will be low. At high temperature, adsorption will be low, that means temperature has to be low to have more adsorption, and also the dimensional change. Dimensional change we will discuss. So, with this condition we can achieve the adsorption. With the increase in fiber swelling, so the dimensional change we are discussing, as the moisture gets absorbed. So, dimensional that fiber swelling, the capillary channel between the fiber gets reduced, which result lower vapor transmission. So, capillary that means the pores will get reduced. So, that will affect the moisture flow. The distortion caused by the fiber swelling results in built up of internal stress, which acts as the which affect the moisture adsorption process. So, if the internal pressure is more, the moisture adsorption process will get affected. The adsorption hysteresis increases with the increase in hydrophilicity of the fiber. So, that way we have seen the adsorption hysteresis, if it increases, that means sorption hysteresis increases, the adsorption will be lower. And last principle is the forced convection. The transmission through forced convection takes place when the air is flowing. The amount of moisture transmission in this principle is governed by the difference in moisture concentration between the surrounding atmosphere and the source. So, that is the governing principle, and this is the same as the diffusion, that moisture concentration difference has to be there. But in diffusion, the moisture gradient, pressure gradient was the only source of transmission, but here in addition to that, that is the surrounding atmospheric moisture concentration in the surrounding atmosphere, and Ca is the in the source, that is the in the clothing case it is the skin humidity. This is the equation where Qm is the mass of moisture vapor transmitted by convection through the fabric with an area A, area of the A fabric, and H and Ca is the moisture concentration of the fabric surface, which is high enough, higher than the atmosphere. So, that moisture gradient pressure gradient is created, and the rate of moisture transmission can be controlled by the difference in vapor concentration. So, that this is the difference in pressure concentration and the mass transfer coefficient Hm, which depends on the fluid property, that is on the viscosity of the fluid. So, this is the mass transmission coefficient here. So, in windy atmosphere, the convection method, this is forced convection method, plays a very significant role in transmitting moisture from skin to the atmosphere through the clothing. So, we will see one method we have developed. In that method, if we have tried to see that the effect of the wind blowing, how the speed of flowing air affect the moisture transmission. So, now we will see the few research study. So, in this study, in what we have developed different fabrics of polyester viscose. The same fabrics we have discussed in last class, that the liquid to water transmission, wicking. In wicking, what we have seen, with the increase in viscous content. So, viscous content is increased from 20% to 100%, that in 20% means 20% viscous, 80% polyester. So, as the in earlier case in liquid moisture transmission, what we have observed, as we increase the viscous content, the wicking rate reduces, and that is we have seen that is due to the water gets actually attracted by the hydrophilic fiber, and which slows down the wicking. But in case of moisture in vapor form, it is also in a moisture, but it is in vapor form. Here the same fabric shows the reverse trend, means as we increase the viscous content, that means here the polyester content is reduced. So, as we increase the viscous content, the relative water vapor permeability increases at very high rate. So, from say 58% to 62%. So, relative water vapor permeability increases. So, this is basically, so with the increase in viscous percent PV in PV fabric, polyester viscous blended fabric, water vapor permeability of fabric increases, and mass per unit area of all fabrics are constant. So, this the fabric, all the fabrics, if we see, the fabrics mass per unit areas are constant, their porosities are constant, the pore structures are constant. That means, if we see the same fabrics with air permeability, they have this almost same air permeability, there is no change in air permeability, which shows that air pockets, air open cover factors of the fabrics are same. But here the fabrics, that means pore structures are same, for the same, that means this is not directly related with the air permeability. So, moisture vapor permeability here it is increasing, and that is mainly due to the non-Fickian diffusion here. Here viscose being the it is a hydrophilic fiber, it absorbs the moisture and it gets transmitted. So, moisture absorption, desorption and non-Fickian diffusion comes into picture here. And if you see the absolute moisture vapor resistance, it reduces with the increase in viscous content. So, this is a very interesting trend, which shows that at lower activity level, when the moisture transmission is in the vapor form, we have to go for higher hydrophilic content. But when the moisture transmission is in liquid form at higher activity level, then we have to go for the hydrophobic fiber. Okay. So, the difference in the water vapor permeability of the fabric occurs because of something else rather than openness of structure. When the vapor transmits through the textile layer, two processes are involved, the diffusion and sorption desorption. The water vapor diffuses through a textile structure in two ways: simple diffusion through air space and between the fibers and yarn, and along the fiber itself, non-Fickian diffusion. So, Fickian and non-Fickian diffusion we have discussed. At a specific concentration gradient which we have maintained, the diffusion rate along the textile material depend on the porosity of the material that we have already discussed, also to the water vapor diffusivity of the fiber. The diffusivity of the textile material increases with the increase in moisture regain, that we have already seen. So, that is why the diffusivity increases here. So, as the fabric set and structure of all fabrics almost same, the diffusion through air should not differ. So, that diffusion through air, that Fickian diffusion should be constant. So, here it is actually in this case when the viscous content is increased, it is other than the Fickian diffusion. So, as the viscous proportion in the fabric increases, moisture regain of the material increases, causing the higher diffusivity. So, due to increase in diffusivity, it is increasing. Okay. As the same way, moisture transmission through sorption desorption process increases with the increase in hydrophilicity of fiber. So, here the in this particular case, when the porosity of the fabrics are same, only the hydrophilicity of the fibers increases. In that case, the Fickian diffusion is not there, non-Fickian diffusion and sorption desorption comes into picture, which is at lower level high hydrophilic fiber like cotton, viscose fiber is actually suitable for that, for low activity level. So, hygroscopic fabric absorbs water vapor from humid air close to the sweating skin and releases at the dry. This already we have discussed. Okay. Fabric with the less hygroscopicity provide higher resistance of air. So, this will continue in the next session. Till then, goodbye. Thank you.